I don't know if this would be interesting to anybody, but this is the MCS 8085 User's Manual. I just kind of wanted to briefly go over it because it's interesting to me. It says here October 1979, so let's go ahead and open it up. And as a reminder here, this is right before the x86 architecture is developed by Intel. Here's our table of contents. It looks like chapter 1's just a introduction to the functions of a computer. That's kind of funny. And the x86 manual, their first chapter is an introduction to the manual, like how the manual works. This one starts off by telling you how a computer works. Then it's going to tell us about the MCS 85 architecture, so that's cool. Then it goes on to talk about the other chapters. It looks like when we get to chapter 6, things start getting really deep. In chapter 6, we have device specifications. So here's an MCS 85, MCS 80. We'll have system support components. Over here is peripheral stuff. The only time I saw this word static RAMs is when I was researching the beginning of the company of Intel itself. They came out with the 1001 static RAM. This ended, I guess, magnetic core memory. Then we'll get read-only memory stuff and EEPROMs. By the time we get to chapter 7, we get to see some development aids, something called an in-circuit emulator. That sounds pretty cool. And then the appendix, so that's pretty short and sweet right there. Here's chapter 1. I won't read these, but I think just reading the subtitles and maybe talking out loud would be beneficial. Be sure to follow this link if you want to read it on your own. You can find it on archive.org. So, it talks about a typical computer system. You got your CPU, you got memory, and you got input and output. Yep, sounds about right to me. Now, the architecture of a CPU is what's really interesting, and that, for me, begins the complexity of the whole system. I like how they break it apart in terms of you have registers and ALU, and then control circuitry. I assume that has to do with the clock. So one of the most important registers is the accumulator. This subtitle says program counter, so this is where we read about jumps and subroutines in the stack. It's kind of cool to think about. Programmers have been manipulating the stack since 1979 and probably even before. When you get down here, you'll read about instruction register and decoder. Funny to see this sentence. The characteristic 8-bit field is often referred to as a byte. Yep, that's what 8 bits make. And then you get the code itself. They call it operation code. This is an 8-bit word used as an instruction code, which apparently can give the computer 256 alternative actions to execute, but I don't necessarily think it uses all 256 possibilities. This is really well worded. I know I said I wouldn't really read much to you, but it says the processor fetches an instruction in 2 distinct operations. First, the processor transmits the address in its program counter to memory. Then the memory returns the address byte to the processor. The CPU stores this instruction byte in a register known as the instruction register and uses it to direct activities during the remainder of the instruction execution. Alright, so here's some information on address registers. They'll talk about the arithmetic logic unit, then talk about control circuitry, computer operations such as timing, instruction fetch, memory read, memory write, and then wait for the purpose of memory synchronization, which is pretty cool. It says the speed of the processing cycle is limited by the memory's access time. Next up is input-output stuff. It'll tell us about interrupts, it'll tell us about hold. Nice little diagram of the CPU module, like there's memory, here's your address bus, here's your control bus. All these things are working together with the CPU, so some computation can occur. Here's part 2. This is an introduction to MCS 85 now. Alright, so here's a brief introduction to the philosophy behind MCS 85. Basically, it gives the 8088 user increased performance and decreased component count, so very good. They'll begin explaining the evolution starting in December 1971. Here's an interesting chart where they give us the 1973 date, and then into 1974 the number of instruction cycles seems to decrease dramatically, then it stays the same and decreases a little bit and decreases a little bit until we get to this date of 1978. And then they draw a nice box for us of programs going to system, I don't understand how those boxes help us understand anything at all. But here, these are the diagrams I like. Especially this one right over here. Here's the CPU, here is the I/O, and down here we see a connection to ROM and EEPROM. More information over here on peripherals, then a paragraph on interfacing to standard memory, demultiplexing the bus. Over here they talk about system performance and that the true benchmark of any microcomputer system is the amount of tasks that can be performed by the system in a given period of time. So, interesting definition of performance, and obviously we can ask the computer to do several different tasks, several different types of tasks. So in that sense, performance sure can be subjective. Distributed processing is a good thing. Instruction cycle access time is important. Right here they say, a close look at the MCS 85 bus operation shows that the access requirement for this speed is only 575 nanoseconds. Geez, I don't know how we can time things at that low level. And that's why I'm not a computer scientist, I'm just a techie trying to barely hang on to all these concepts. Well, now they're going to talk about the 8085A. Say it's an 8-bit general purpose microprocessor, so wow, only 8 bits, huh? Then they say at the same time it is capable of accessing up to 64 kilobytes of memory and has status lines for controlling large systems. Here's a good diagram of what this subtitle says, what's in the 8085A. Really cool to see the information about registers, especially after I just read the x86 description of registers. Here it says the accumulator is the focus of all the accumulator instructions, which include arithmetic, logic, load and store, and I/O instructions. It is an 8-bit register only. The program counter points to the memory location of the next instruction to be executed. It always contains a 16-bit address. So I vaguely remember seeing this chip is a 8/16-bit instruction set. Maybe that's why. Now your general purpose registers B, C, D, E, and HL may be used as 6 8-bit registers or as 3 16-bit registers interchangeably, depending on the instructions being performed. So that's a cool feature. You got a data pointer, a stack pointer, your flag register. Here's information about the flags. And I find it funny that they show you things like this, the binary and then the hexadecimal. My students totally understand the concept of a carry bit. At least they do when they finish my Intro to PC Applications class. But when you put hexadecimal in this form, that is not very clear. But then again, if you're reading this, you're probably at that really high level and actually understand how the hexadecimal is added in that way. Alright, so let me speed this along. We got a few other flags, the auxiliary carry flag, a sign flag for, negative numbers. You have a 0 flag, a parity flag, which is good for error correction, or at least error identification. Then they start talking about the stack. Alright, I'm going to try to start moving a little faster here, just flipping through the pages of this MCS 80 manual. Just really cool. They're gonna take things down to the lowest level for you to see. And look at that, I just barely got to chapter 3. So maybe it's worth your time if you're a history connoisseur to look at something like this. I always enjoy a good die picture myself, but I'm not sure how useful any of this information will be, especially to people interested in low-level programming on x86 architecture. But if you're interested in comparing this manual to the x86 manual, I think it's kind of cool to browse through. Remember, this is 1979 here. And without this 8080 stepping stone, we wouldn't get to our 8086. Well, think about 8085 and then 8086. Oh, look at those logic gates. I love myself some logic gates. Oh, I had to stop at this section. So it's talking about read mode, standby mode. That's one of the first things the x86 manual talks about, is the modes that the chip can be put into. But when I saw programming here, I wanted to read that real quick. Initially, and after each erasure, all bits of the 2732 are in the 1 state. Data is introduced by selectively programming zeros into the desired bit locations. Although only zeros will be programmed, both ones and zeros can be presented in the data word. The only way to change a 0 to a 1 is by ultraviolet light erasure. Whoa, that is cool. Alright, so then this entire section of the 2758 talks about that UV erasable low power PROM. High speed PROM, another programming title, so... Oh, bipolar PROM. This chip must have problems. Oh, here's our in-circuit emulator. Universal PROM programmer. Look at those floppy disks. Alright, here's some source code. This is really cool, the amount of code they have in the manual itself. So I'm on page 414 here, and it looks like they stop with a page that says CRT and cassette code. Let me go back just a little bit. Okay, that's the same thing. So these are the codes you type in to do certain things. Over here we'll see our move command, push, there's a move, and then this is really hard to read. But then if we keep going back here, we have some temperature sensor codes that is absolutely hard to read. I suppose I could zoom in, but I think that is enough for today. Thanks for watching this video. Really a strange one. MCS 8085 user manual, but I hoped you learned a little bit. I did.